Hi everyone, my name is Biruk. I'm a PhD student at the Scuola Superiore Sant'Anna here in Pisa. And today I'll be presenting you our work, which is related to the design flow of dynamic partial reconfigurable systems on hardware software co-design for NFPGA SoCs. This work was done in collaboration with Marco Pagani, Alessandro Biondi, and Giorgio Buttazzo. Okay, before we discuss about dynamic partial reconfiguration, let's talk about FPGA-based system on chips. These systems, which have been popular in the past couple of years, integrate CPUs and programmable logic onto the same chip. This allows them to combine the best of these two worlds, meaning they bring in the reprogrammability from the CPU world, and they also bring in reconfigurability from the FPGA world. And they allow to build very powerful and flexible systems. Over the years, designing for these platforms has been getting easier and easier due to the availability of lots of design tools, both from the vendors and as well as from the open source hardware community. Okay, so what is dynamic partial reconfiguration? This is a feature offered by these platforms. It is basically the ability to modify or change some of the functional blocks running on the FPGA at runtime. It gives us a flexibility not to configure the full FPGA when we want to modify a certain section of the FPGA. So basically we can swap in and swap out hardware accelerators on the fly. Dynamic partial reconfiguration, or DPR, also gives us the possibility to time multiplex hardware modules, given that our accelerators are not going to be running on the FPGA all at the same time. We can use some sort of time multiplexing to configure our accelerators onto the FPGA, therefore reducing power, the cost of the FPGA, as well as the size of the FPGA. And finally, DPR systems also allows us to remotely configure our systems or remotely update or extend our systems because they support the modification of a section of the design without interrupting or losing communication. Okay, now we discussed dynamic partial reconfiguration in on itself, and let's discuss about it under the context of hardware software co-design under real-time safety critical systems. So safety critical systems are composed of software components and hardware components. The software components are mapped onto the CPU, and the hardware components are mapped onto the FPGA accelerators. And the idea behind using a co-design approach for safety critical systems is to offload computationally demanding functions onto the FPGA and therefore improve the performance of our application. In real-time safety critical systems designed using a co-design approach under DPR, there are software tasks and there are hardware tasks. The software tasks are characterized by some timing-related behaviors, such as activation time, deadline, and worst-case execution time. Meanwhile, the hardware tasks are characterized by execution time and resource consumption of the hardware. So how do we use these systems, these hardware software co-designed real-time safety critical systems? How do we use them under the consideration of DPR? So usually this involves a bunch of software tasks invoking or asking for an acceleration request on the FPGA, and then a reconfiguration interface which configures or loads the accelerator onto the FPGA. So at the beginning, we will start this discussion with a software task which contains one software task and two hardware accelerators. So the software tasks starts execution, and at some point it invokes a request for hardware acceleration. And then as soon as the request is received, it's configured onto the FPGA, and finally the hardware hardware task starts to run on the FPGA. When the hardware task finishes, the software is notified and it continues its execution. It can ask different acceleration at a future time. So this simple example represents what could be a use case for a DPR-based hardware software co-design in safety critical systems. But this is obviously a very simple example, and as you can imagine, when we increase the number of software tasks and hardware tasks, the design of such systems becomes much more complicated. And the design is also strongly correlated with the timing requirements or the timing behavior of software tasks and also the hardware tasks. Okay, so far we have discussed what DPR is and what a hardware software co-designed system under DPR looks like. So what are the limiting factors or the challenges related to using these kinds of systems in our design? The first challenge is related to the complexity of the DPR design flow and the lack of full automation. So none of the vendor tools, as far as we know, fully automate the DPR design flow, meaning there are some manual steps which should be done by the designer. And these manual steps are performance determining steps. Therefore, they require someone with an expertise on FPGA design. The other major challenge in using these kinds of systems is the lack of integration of software task requirements into the hardware flow. The example we saw before considers software-related timing requirements into the design, but none of such integration is supported by the vendor tools. So our solution for this problem, in order to overcome this challenge, is proposing a tool that fully automates the design flow under DPR for hardware software co-design real-time systems. The tool is called Dart and has the following features. In Dart, a designer does not have to be well-versed with FPGA design in order to use the DPR features. They just need to bring in the source file of the accelerators, some timing requirements of the software, and then a description of the FPGA. And then with just a single click of a button, they will be able to create the design and generate the final full and partial bit streams of the design. So Dart abstracts the bit stream generation of the DPR design. It also automates the synthesis, implementation, and bit stream generations of the vendor, the DPR flow, by collaborating with the vendor tools. It solves the previously stated manual design steps using an optimization and MyLP-based optimization. It also generates the static part of the design. I will talk about the static part of the design in just a few slides. And finally, Dart also enables a diagnostic tool which allows it to diagnose errors and tries to correct them. How this works is basically if there is an error, Dart detects it and then tries to change some parameters in the optimization engine such that this error will be mitigated in the next iteration. Okay, so far we have seen the challenges related to DPR and how Dart, our tool, is able to solve these challenges. So now let's look at a little bit in depth what constitutes a DPR design. A DPR design is composed of reconfigurable regions, which are regions on the FPGA fabric, which are used for placing the accelerators. The reconfigurable modules are the accelerators, which are swapped in and out at runtime, and the static part of the design, which is the unmodified version or portion of the FPGA DPR design. So the static part usually contains communication interfaces, audio and video engines, and etc., things which should not be modified at runtime. The outputs of a DPR flow are full and partial bit streams. We discussed about the complexity of DPR flow, but so how does it actually look like? So as we said before, DPR flow contains a lot of bunch of manual design steps. One of them is, for example, floor planning, which is not automated in most vendor tools. It involves assigning the partition or the placements for the reconfigurable regions. And in general, a DPR flow is an iterative implementation. It involves an iterative implementation. What this means is, first, we decide the floor plan for the reconfigurable region. And in the first iteration, we implement, meaning we place and route the static part with the first group of reconfigurable modules. And then in the next iterations or in the following iterations, we only place and route the reconfigurable regions, the remaining reconfigurable regions. DPR flow by itself is very complicated, but when we use it in the context of hardware software co-designed real-time systems, it becomes even more complicated because of the addition of additional design steps, namely the logic partitioning. Logic partitioning means allocating hardware tasks into reconfigurable regions. As we see from this example, these two reconfigurable regions are allocated to this region, and these two reconfigurable modules are allocated to this reconfigurable region. This allocation or this partitioning is done by using the software timing attributes as well as other parameters of the design. Okay, so far we have seen what makes a DPR design more complicated normally, and then when it's combined with in the context of a co-design flow. Now we look how Dart actually works and how it's solved, how this complication is alleviated inside Dart. Okay, Dart is composed of 4 design stages. The first stage is called processing stage, which takes in the inputs from the designer, which are the source files for the accelerators, description of the FPGA, and the timing requirements, and then synthesizes the modules, extracts the resource requirements of the modules, and then passes it to the next level, which is a partitioning and floor planning stage. Inside Dart, partitioning and floor planning are solved together, meaning they are merged into a single optimization problem, and their solution is guaranteed to be globally optimal. In fact, the reason for merging those two into a single optimization problem was to guarantee the optimality of the solution. So this block, MILP implementation block, contains a set of constraints which are related to floor planning, the timing constraints, as well as some vendor-related constraints. All of these are formulated into an MILP, C++ implementation of MILP. And finally, the MILP also supports objective functions and allows the designer also to define the objective functions they want. The outputs of the second stage, the partitioning and the floor planning stage, are passed to the third stage, which is a static part generation stage. So the static part, as we said before, is a part of the design which is not subject for reconfiguration. So this part contains usually, as we said before, communication interfaces, communication buses with the peripherals, as well as with the processor and memory and so on. So all of these hardware modules are generated by Dart, depending on the type of design. Finally, there is the implementation stage, which performs the iterative place and route we discussed before, using Tcl scripts generated also in this stage. The outputs of this stage are full and partial bit streams of the design. Remember that the diagnostic stage, where errors in design, in case they appear, are also performed here. The diagnostics is also performed in this stage. Okay, so far we discussed about the complexities related to integrating a DPR approach in hardware software co-design of real-time safety critical systems. We discussed the challenges. We discussed how our tool, Dart, is able to solve this. We also saw how Dart works, or the internal workings of Dart. Now we discuss about the experimental evaluations we performed to test our tool. So the objective of our experiment was twofold. The first one was to test the feasibility to see if Dart actually generates designs which are useful in the real world application. The second one is related to testing the performance of Dart against a standard DPR flow. Standard DPR flow meaning the flow dictated by the vendors, which also includes the manual design steps. So the evaluation was performed on the Pink Z1 platform, which contains the SAC'21 system on chip with RTX FPGA and dual-core ARM Cortex-A9. So in order to perform our test, we created a case study for a reconfigurable image processing system, which involved 2 neural network accelerators, which were binarized or fully binarized neural network accelerators obtained from the FIN framework. The first one is a convolutional binarized neural network accelerator inspired by VGG16. It was running on the CFAR10 dataset, and it also used 1 bit for the weights and the activation. The other accelerator was a fully connected neural network, which contained 4 fully connected layers, also used 1 bit for the weights and activation, but trained on the MNIST dataset. Both accelerators were operating on a batch size of 256 images, meaning in each acceleration invocation, they perform inference on 256 images. The other input hardware accelerators are filter IPs obtained from Vivado HLS. They were FastX, the Gaussian, and the FIR filters with a batch size of 24 images on 176 by 144 pixel images on each acceleration request. The software part of the case study also involved 3 software tasks, each having their own timing requirements and each associated with a specific hardware accelerator. Okay, before we go into the experimental results, let's just stop and realize how the case study was able to improve design productivity. So in this case study, imagine a designer which has no expertise on FPGA or on DPR. So what they did is they brought in source files of IPs or the filter IPs, also the source files for the neural network implementation. They can be obtained from HLS or RTL implementations. And also they brought in a software requirements. And then with just a single button click, Dart is able to automate the full process of the DPR flow and generate the final bit streams of the design. The designer doesn't have to know anything about FPGAs, but they can fully utilize FPGAs and DPR at the same time. So this is a level of productivity provided by Dart. Okay, now we go to the results. Dart, based on the timing inputs, partitioned the design into 2 reconfigurable regions. In the first reconfigurable regions, there were the 2 hardware accelerators for the neural networks, and in the second accelerator, or in the second reconfigurable region, there were the 3 IP accelerators. Dart also generated the static part of the design. In this case, each reconfigurable region had 1 AXI master bus and 1 AXI4 Lite slave interface for commands. And they also had an interrupt line. Dart also generated a decoupler IP in order to decouple the reconfigurable regions from glitches during reconfiguration. So the first result is post-synthesis resource consumption of the reconfigurable regions, the reconfigurable modules. So as we mentioned before, the size of the reconfigurable region is determined by the resource reconfiguration or the resource consumption of the IPs or accelerator hosted in that region. So in this case, for example, the LUTs, the amount of LUTs or lookup tables there should be in the second reconfigurable region should be above this value because this is the maximum. And also the number of flip-flops should be above this value. The number of VRAMs should be above this value, and the DSPs should be above this value because the reconfigurable module with the maximum resource consumption in that reconfigurable region determines the size of the reconfigurable region. The same for the first reconfigurable region. Okay, here we depict the execution time of the reconfigurable modules. Again, for example, if we consider the 3 filter IPs, they were executed way below the timing requirements of the software task. They were executing with the same for the 2 filter IP, the 2 neural network accelerators. So both of in both reconfigurable regions, timing was not violated or deadline was not violated. Finally, we compared Dart with a manual approach using the Xilinx flow in the standard Xilinx flow for dynamic partial reconfigurations. And even in this case, we were able to achieve a 2% improvement in total design runtime, which means our design ran faster than the standard DPR flow from Xilinx. Conclusions. Dart is a tool. In this presentation, we presented Dart, which is a tool for full automation of design flow in real-time dynamic partial reconfiguration based co-designed systems. It fully automates the design flow and improves productivity very much. Dart works on Xilinx FPGAs, and it has been tested to automate a real case study, real-world application involving reconfigurable image processing system. Thank you for listening my presentation, and please, if you have questions, you are very welcome. Thank you.